Ladies and gentlemen, so my name is Shaun McQuaid. I'm with Mercury Systems. I am obliged both by Mercury rules and regulations as well as my own personal code of conduct and honor to inform you I am aware of the fact that I am standing between us and lunch. So I feel that it's important that we're all on the same page here and that we all continue to move forward. The title of the talk here, which should take up most of the talk, is Leveraging the Best Commercial Innovations with an Open System Architecture Approach in High-Performance Embedded Computing Subsystems. I can always tell it's a new year because it's 2016 now, which means we've got a new marketing template for our slide decks, which have gone from real pictures to cartoons, which is more my speed. So I feel confident that we're moving in the right direction here. So when we started to put together the talk we wanted to give here, it struck me that having the right analogy for this kind of a conversation is actually a big part of what makes this work for us. And after a little bit of back and forth with some of the elite marketing team that Mercury can bring to bear here, we came up with a kind of a tree analogy. The idea being that if you're looking at a high-performance embedded computing system, there's really 4 major branches that you need to think about when you're trying to put this together. So interoperability from electromechanical level, switch fabrics and I/O, rugged packaging and cooling, and performance and assurance. So if you kind of look at those as the major branches, each of those has minor branches that come out from there. But at the root of all of this, aptly enough, are the standards that are embodied in the VITA organization. And so you can kind of see through this analogy how those roots kind of feed up into the tree architecture here. And I think it's important to point out that the analogy holds all the way down to what the function of roots are, right? There's 2 main functions of the root of a tree. One of those is to actually anchor the tree so that it doesn't get tipped over as the winds of change blow. And the other real function there is to provide nourishment for the organism, which I believe is very analogous with the way that the standards body functions, in that the best and the brightest come together and feed in the best data, test results, all of the back and forth that happens, negotiation, and at the end of the day, the tree gets nourished to the point where we actually have some good capabilities. So that's kind of the analogy that we're operating under at this point, and hopefully that'll make some sense as we go forward here. So again, this is really, the tree analogy is all we'll see, right? I'm trying to stay away from digging deep into some of the product details. I think we've had quite a few people who have done that admirably already. You don't need me to dig into there. But the 3 key pieces that I look at when it comes to interoperability is portability, upgradability, and scalability, which are a lot of abilities and a good tongue twister. But this comes back to, where does a standard actually come into play, and how do you actually leverage it so that you can maintain all of these features going forward? I look at VME as the poster child for electromechanical interoperability. VME was very successful, continues to be very successful. And part of the reason why that's the case is because it was architected up front for portability and growth, right? There was a lot of capability to expand what VME was capable of over time without violating the standard. There was enough flexibility built into user I/O so that you could actually adapt the standard to map against certain requirements of a variety of systems across a variety of markets, right? Some of which we already discussed today. And VPX is the same way, right? There's been a significant amount of effort gone into making it an open standard that's easily upgradable, that allows for growth as signal integrity challenges come forth, as signal speeds increase, as more processing capabilities are brought to bear. So that's part of the benefit that I believe the standards body brings as far as interoperability is concerned and as far as portability is concerned. Upgradability is another piece of that. We're seeing that right now with some of the upgrades of the standards, such as FMC. We already mentioned about some of the growth that's going on there. Some of the OpenVPX profiles that are adding higher speed capabilities for PCIe Gen 3, for higher speed InfiniBand rates, Ethernet up at 10 gig, 40 gig. There's growth and paths to the future there. Again, a lot of what has been discussed today has focused on that. And then the other piece of the puzzle is scalability. And with the growth of high-speed fabrics, switching capabilities, some of the software innovations that we've discussed, some of the stuff that we kind of have brought to bear, that allows scalability. And it's not just scalability as an idea of adding more boards and having your system survive and your software not grow out of proportion or grow strange tendrils that that don't necessarily make sense. It's also scalability across form factors. So the ability to actually take an engineered block, whether that be a hardware block or a software block, and migrate that down to a 3U solution, or even further down to a VNX or VITA, one of the VITA 73, 74, 75 small standards, all the way up to a 6U OpenVPX kind of an architecture, or even further up to ATCA. That's actually not just a value proposition for the people who are doing the work, not having to redo the work over and over again. I believe it's also a value proposition to the customers who are actually looking to leverage these capabilities, because it means that they can actually leverage application work that they've done, that they can leverage from program to program the capabilities that they've developed. And I think that's a big piece of what this interoperability at the electrical mechanical level brings to bear. So of course, packaging becomes a part of the story. Packaging brings to bear the processing and the size, weight, and power performance that you need in order to actually take these kind of capabilities and deploy them in the embedded sense. I look at the data centers that run behind the back rooms of Amazon and Google. What are those made up of? And we talk about the leveraging of that kind of a cloud architecture, fog computing, cloud computing, up to the future. All of those guys are using the highest of the high-end processors, right? The Xeon class, E5, E7 series. They're not piddling around with the kind of processors that you see in a laptop or anything along those lines. The only way that those kind of capabilities can be deployed in the kind of markets that we live in is if the packaging is up to snuff. And I'm not just talking about air-cooled or conduction-cooled, 48.1, 48.2. Some of the new developments in liquid cooling, so the liquid flow-through capabilities. Some of the developments in airflow through and airflow by, 48.5 and 48.7, bring this to bear. Without those kind of capabilities in place, it's going to be difficult to deploy these technologies, at least in the way that they were intended. And of course, the most efficient use of commercial technology is to actually pick it up and put it down without having to do a lot of adaptation and adoption to try and make it fit into the embedded world. And again, coming back to the theme of the standards, the way that I look at this is that if we've built in the flexibility that allows you to actually develop this innovation, then you're going to be in a better position. A good example of that, even going back to conduction cooling, standard conduction cooling is the VITA 48.2 standard. There's opportunities there to keep within that mechanical form factor, but do development to try and make things more efficient. Mercury invested in wedge lock technology at one point that allows us to actually reduce the amount of temperature drop as you go through that wedge lock and make it a much more efficient interface. That's completely within the realm of the standards body, and it completely complies with any chassis you could put it into. It's just a more efficient solution. And that's a good example of having a standard that allows that capability, allows that innovation, without having to redo the whole chassis. There was a couple other examples that were put forth today, particularly around things like the ATCA chassis. Again, the flexibility that's built into these standards is what allows us to grow as we go forward here. So switch fabrics and I/O. This is an interesting one because I remember, it's been several years since I was on the playground, but I do remember sitting at the bottom of a seesaw and if you don't have someone on the other side who's equally balanced with you, you're probably not going to have a lot of fun in those games. I look at processing and I/O as the two ends of the seesaw, and unless they're balanced and they can play back and forth, you're not necessarily going to have much fun building up a system. So switch fabrics and I/O kind of are tied together in that sense. The idea that you can develop unrestricted performance, that you can develop an interface that allows you to operate without errors or with minimal errors is a big piece of the puzzle. We've talked already about this a couple of times today, where we look at the bandwidth and the error rate when you're talking about PCIe Gen 3 rates up at 8 gigabaud, or when you're talking about 10 KR Ethernet up at 10 3/8. Without the time that you invest in the kind of backplane architecture, and not just the backplane, but the module and the whole channel, all the way from an XMC-based FPGA that's streaming data, you have to go through an XMC connector, you have to go through the module, you have to go through the backplane, you have to go through the other side of the connection. It's a full channel kind of spectrum that you have to worry about. That's the piece of the puzzle that's needed to actually bring to bear the next generation of switch fabrics and I/O. Refreshable is another piece of the puzzle that comes to bear. And I know I keep saying this is a piece of the puzzle and that piece of the puzzle, but I think there's a lot of pieces of the puzzle that come together. Again, we saw that earlier. I look at let's look at the cloud and some of the tactical data centers that are out there. Our friends at Microsoft, for their cloud architecture, are actually moving away from ASIC-based NICs. They're moving towards an FPGA-based infrastructure for their network interfaces. And the primary driver there is it takes too long for them to go and upgrade every NIC in the data center where there's thousands and thousands of boxes to go from 1 gig to 10 gig or from 10 gig to 40 gig as far as Ethernet is concerned. So they're looking to put down an FPGA-based solution so that you can actually migrate with simply a firmware load. This is something that we're very familiar with, having bonded FPGAs and Intel processors at Mercury for about 6 or 7 years now. That's, again, one of the reasons why we're also very excited about the Intel-Altera merger that just finalized last month. And finally, at the end of the day, it's that assurance of that channel from start to finish that makes it possible for you to take advantage of those I/O channels that are in place. So. The final piece of the puzzle, performance and assurance. And from this perspective, I'm really talking about the trusted nature of your architecture and the trusted nature of your supply chain. All of this is for naught if at the end of the day, you can't trust your supply chain to deliver you a system that's made up of pieces that you can trace the capabilities of, you can trace the manufacturing sources of, you know that you aren't dealing with a counterfeit issue or something along those lines. So having the ability to do that from your supply chain perspective, as well as having hooks and handles in the foundation of what you bring to bear so that you can deliver a personalized system integrity solution. That's another piece of the puzzle that we bring to bear and that I think a lot of the folks in this room have some experience with these days. I think that from my perspective, that's kind of, it's the roots in the tree analogy that comes back to from my perspective. Without the roots and the standards, without the kind of collapse of information in the standards body that all of the folks who play here bring to bear, we don't end up with a solution that's scalable and extensible. I think that without those roots anchor us, those roots help us to grow. And I think that the tree is healthy, there's a lot of capability out there, and there's a lot of work that's being done.